Okay, thank you, Cody. Yes, so I will tell you something about 60 SCFTs and integrable spin chains, which is based on some, would you like, later, which is based on some recent work from July this year, this archive link here, with Laurent Bohm and Jonathan Heckman. So I'm giving this talk at this string theory seminar series on Zoom, which I think has been a great thing throughout this summer for keeping everyone together. So I just wanted to thank John and Cody for organizing this, and I hope it keeps going. Okay, so the first thing I'm going to tell you about is why am I talking about 60 SCFTs and integrable spin chains? So what is my motivation? In fact, if you want to be a little bit more meta about it, I can tell you why am I talking about 60 SCFTs at a string pheno seminar, which I'm sure is the question that at least some of you are thinking. And the answer is a fairly obvious one, which is that for understanding things like string phenomenology, I'm interested in quantum field theory. But quantum field theory tends to have a lot of questions which are very hard to answer. And so I would like to study a more constrained system, which I get from considering something like quantum field theory, plus some more symmetries. And in my case, I want to consider supersymmetry and conformal symmetry. So if I add these two additional symmetries to my quantum field theory, then there are a lot of questions which I might want to ask, physical questions, and these become tractable only in this setting, or become tractable specifically in this setting. And hopefully we can take the lessons that we learn here and see what we can learn about the case without these additional symmetries. Okay, so what kind of questions might we want to answer? Well, we might like to be able to compute correlation functions. Correlation functions are like expectation values of observables. These are very physical objects that we would want to compute in any quantum field theory. And in a conformal field theory, correlation functions of local operators are in part governed by the scaling dimensions of operators, which is essentially just their 2-point functions. And this is considered to be part of the CFT data. So I hope that you can see my mouse when I like circle things. If not, this is going to be somewhat confusing. Okay, so I've told you why I might be interested in the SCFT part of the title. What about the 60 part of the title? Why 60? So in 60, we are very fortunate because there is a vast number. Since I recently worked it out, I can tell you the actual numbers. They're particularly interesting, or particularly, sort of good to get a handle on this. There's roughly 10,000 infinite series of these 60 SCFTs, plus a few 10,000 sporadic examples. And these CFTs have geometric realizations from string theory, or more specifically F theory, which was given about 5 years ago in this paper by Heckman, Morrison, Rodelli, Espafa. And this is really a geometric construction. And the geometric construction contains a lot of information. It tells you lots about sort of deformations of the moduli space of the theory and so on and so forth. However, from this particular geometric construction, one thing which is very unclear is how to read off dimensions of operators. We've already told you that dimensions of operators are vital for computing correlation functions, so this seems like something that we would want to compute. So I would say my overall motivation for studying 60 SCFTs is I want to understand correlation functions in quantum field theory, and this is a setting where I have a huge number of examples of superconformal field theory, and we might be able to find some way of understanding the operator dimensions from these very detailed geometric pictures. Okay. So let me just give you the contents. So first of all, we're going to do kind of a lightning review of 60 SCFTs and their construction from Calabi-Yau geometry. And I'll tell you a little bit about what's known of the spectrum of these inherently strongly coupled theories, and also what you can say about their operator dimensions, which it turns out to be a somewhat limited thing at the moment. However, that will be a lightning review because I want to spend the bulk of the time talking about the example that we considered in the paper with Baum and Heckman, which was the rank R conformal matter and an integrable sector. So I'll explain where the integrable sector comes from and so on when we get there. And the question that I want you to be thinking about is, what are the operator dimensions that we can compute in these theories? And then I'll give some conclusions. So I've positioned this talk as sort of a story telling you about operator dimensions because these are interesting for correlation functions. But actually, when you get to the end, if you want a takeaway message, the operator dimensions are actually not so important compared to the fact that you find that there is at least a sector of these theories which is controlled by an integrable structure, which means that you may be able to do some exact solving of certain parts of this theory. So that kind of comes out as a surprise, but I think a very useful one for being able to compute more aspects of the theory. And I'll talk about that more in the conclusions. Okay. So let's first of all do our lightning review of 60 SCFTs. So in this paper of Heckman, Morrison, Rodelius, and Baffa, they showed that 60 SCFTs, which come from F-theory, essentially all take the form of linear quivers, what were called generalized quivers, where conformal matter, which I'll explain in a moment, acts as the links between the nodes of the quiver. And there are some nonlinear kind of decorations at the end. So the picture that the authors of this paper usually like to produce in slides, which I've sort of hand drawn here, is that you have a bunch of nodes of the quiver, and these are connected by conformal matter links. And at the end, you can have this kind of some other orange things. All the different options for these kind of things are explained in their paper, but the general schema looks something like this. Okay. So it's easy to see that the conformal matter, which acts as the links all the way along the spine of this quiver, sort of behaves like a building block of other 60 SCFTs. So conformal matter was first discussed before this, or earlier, by Del Zotto, Heckman, Tomasiello, and Baffa. And so for the sake of understanding how to build these kind of quivers, it makes sense to first of all understand the conformal matter theories. In particular, if we want to study something like operator dimensions or integrability, the first thing we will study is the building blocks, which is the conformal matter. Okay. So conformal matter behaves like a building block of 60 SCFTs. So what do we know about the spectrum of these conformal matter theories? So in general, conformal matter between two, between two vector multiplets in 6D, or between two gauge groups in 6D, is some strongly coupled object. And so we have to kind of work at it to understand it. However, there are two examples where you have a sort of more of a perturbative handle on it. One is the case where your gauge nodes are both SUN, in which case conformal matter is just matter. It's a bifundamental hypermultiplet. Okay, and inside of a bifundamental hypermultiplet, there exists a scalar. And that scalar is a doublet under the SU2R symmetry. And we'll write the components of the doublet as X and Y dagger for later convenience. Yeah, so we have a scalar field, which is in the bifundamental representation, which transforms into spin 1/2 representation of the R symmetry. Now, for example, we can ask about what I call the SOK conformal matter. Now, for K is greater than 4, this theory is in fact just two half hypermultiplets, one in SOK times SPK minus 4, and one in SPK minus 4 times SOK. So we can actually combine these, which I've kind of schematically written as a tensor product here, and we can see that there is a bifundamental under SOK, basically taken by taking the trace over the SP4 indices of both half hypermultiplet scalars. So you have a field which is now in the three-dimensional representation of the SU2R symmetry. We can call the components of it the triplet x1, x0, and x minus 1. So this is the field which transforms in the S equals 1 representation of the R symmetry. Okay, so if you work at it a bit harder in a way that I will not tell you about because of time constraints, if you analyze the other strongly coupled conformal matter fields, you can see that they have bifundamental scalar fields, which I could call var phi s, which are transforming the spin S representation of SU2R, and have components as usual xs minus 1 all the way down to x minus s. And we find that for GG conformal matter, the choice of group fixes what kind of bifundamental scalar fields that you have. So you see, for example, that for E8, you have a bifundamental scalar which transforms in the spin 3 representation of the SU2R symmetry. Okay. Okay. In addition to having these fields, you also have some interaction terms, at least at one loop. And we essentially have a d-term interaction, which looks something like basically the d-terms are related to certain quadratic polynomials in these scalar fields. So for s equals 1/2, this should not surprise you. For s equals 1/2, what we said was that these x's are just the scalars of a bifundamental hypermultiplet, and now this coupling here is nothing other than the minimal coupling between a 60 hypermultiplet and a vector multiplet. However, for s is greater than 1/2, we expect there's going to be some higher order terms here, because it's no longer just a hypermultiplet, it's some more complicated object. And one way of thinking about this from a stringy point of view is that when you consider sort of GG conformal matter for G is not SUN, then you can think of it as having an M5 brane which kind of fractionates into different pieces. And we expect them to create sort of more complicated higher order interaction terms. But for now, this will do for what we need to compute. Okay, so that was a quick review. So now I want to tell you about an integrable sector of some 60 SCFTs. So I talked about conformal matter, but there's actually an object which I can call rank K conformal matter, or rank K conformal matter of type GG. And that's an object with generalized quiver, where you have the same gauge group on every node, and you have two flavor nodes at the end with the same gauge group. And the blue line here, you remember the link connecting the nodes is nothing other than the minimal conformal matter that we just discussed, or I showed you in the picture earlier. And as we have just seen, at each of the blue links, the minimal conformal matters, there are some bifundamental modes, which we call the xi, mi, depending on the spin. And the spin of the R symmetry just depends on the choice of group of the conformal matter. Okay. So we can start constructing operators. We can consider an operator where we take, so if I label my conformal matter fields, if I label this here as like the first conformal matter, the second conformal matter, and the kth conformal matter, then I can put a subscript depending on which conformal matter it is on this field. And I can construct an operator that looks something like this. And this is an operator which transforms in the bifundamental of G0 times Gk. I should point out that I'm suppressing flavor indices and some summation over flavor indices here for ease. Okay. One example of this operator is where I take all of the mi to be equal to s, in which case I have what's called a pure operator, which this operator itself corresponds actually to a scalar of a d-type superconformal multiplet. which is just a fancy way of saying it's half BPS, and so it's protected, and so its scaling dimension is exactly known because it's exactly equal to its classical scaling dimension. And in that case, it is 4s times k plus 1, where k plus 1 is again the length of this quiver. Okay. The R charge of the operator O pure is k plus 1 times s. So if we have a very, very long quiver, this value is very large. So now let's consider an operator O of the form that I wrote here. And let's consider it only with a small number of impurities. That is, we take almost all of the mi to be s, and some sort of relatively small number of them to be different. Then the R charge of this operator is very, very large when k is very large. Again, because the R charge of the operator is essentially k plus 1 times s. So this occurs when we have very long quivers, and in this context, you could think that perhaps we can treat 1 over r, which is now a very small number, as an expansion parameter, and maybe we can do some kind of perturbation expansion in the R charge, and perhaps we can learn something about this sector of the theory. Okay. So to start with, we're going to focus on AN conformal matter, in which case everything is very easy because I told you that conformal matter is honest, true matter, which is just a bifundamental hypermultiplet, and we can be sort of incredibly explicit about what we're going to do. And later on, we'll generalize this in a kind of surprising way to DD and EE conformal matter. Okay, so for simplicity in this talk, I will focus on the single impurity case, which is essentially where you take all of the s equals 1/2 components, which here I'm now dropping the subscript and just calling them x and y dagger as I did earlier. And I insert exactly one s equals -1/2 component, which I call y dagger. And I insert it at position I, which gives me a set of k operators, k plus 1 operators, OI. So if there is no gauge coupling, then the conformal dimension of this operator is nothing other than its classical dimension, which is 2k plus 1. But of course, we're interested in what happens when we turn on the gauge coupling. When we turn on the gauge coupling, the operators OI with the impurity inserted at position I will mix with the operators OJ with the impurity inserted at position J. And we can see this through the 2-point function of these two operators, which has a form like this, where there is this correction term proportional to this gamma ij, which is the anomalous dimension matrix. So basically that computes how the operator dimensions of these operators differs from their classical values. So we expect this object to be somewhat small. Okay, so at one loop, we can actually use the d-term constraints that I wrote down earlier to compute the this 2-point function. So the first thing to notice, if I go back to that d-term, is that it only contains pairings essentially between I think there's a typo in this part. It contains pairings between basically the I plus 1 and the I terms, or the I minus 1 and the I terms. So essentially you only have nearest neighbor interactions. So for this reason, if J is not I plus or minus 1 or I, then this thing vanishes immediately. And in the case where we take I and I minus 1, you look at what diagrams contribute at one loop, and you find that everything can be captured by some integral. So I don't want to go into the details of this because we have some limited time and it's a little bit technical. But because we're in 6D and we don't really have an honest gauge coupling, we have to be very careful about how we regulate this theory. And in part, the regulation is controlled by the fact that we have this delta kk here. If you want to know more about that, you can look at the paper, for example. I'm just going to brush over it here, but we have to regulate this theory. Okay. So if we now evaluate this integral, we find that the answer looks something like this. So the GI is something like an effective coupling on the tensor branch. The CI tilde is some group theory factor. But essentially what we notice is that the coefficient here of the logarithmic behavior, which by the way follows from the integral, it's by no means imposed by saying that we have this. We simply see it fall out that way, as of course it must. And we can then read off this matrix gamma ij as essentially this object here. This is gamma I minus 1. And similarly, if you work a little bit harder, you can also work out what the correlation is between I, and you get something which looks like this. So in this way, you actually work out the full anomalous dimension matrix from this one loop computation. And you can write this object actually as some 1D lattice Laplacian, which essentially looks like this. So you have some coefficient, which is just the one that we worked out here. And then it's some sort of very simple looking matrix. It's almost diagonal and contains only clearly nearest neighbor terms. But if you stare at this and you think about things you may have learned in the past, you might realize that operator mixing, which is controlled by such a lattice Laplacian, can actually be written as a one-dimensional spin chain with spins plus or minus a half on each of the k plus 1 sites, and it has some Hamiltonian, which has nearest neighbor interactions that look something like this. Well, it looks exactly like this, sorry. And when you look at this, what you realize is, this is precisely the Hamiltonian for the integrable Heisenberg spin chain. So we have discovered some kind of integrability that is controlling operator mixing in this particular class of operators in the sector of the 60 SCFT. So that was a little bit unexpected, but that's very exciting. And I hope to convince you that that's exciting. So we have some complicated statements on the right-hand side here about sort of collections of operators with insertions of impurities. And we can basically just map this to a question about, do we have a one-dimensional spin chain with all spins up? That corresponds to this operator. If we have one down in this position, it corresponds to this operator. And the spin chain Hamiltonian that I wrote down here does nothing other than basically taking this down and swapping it with this up, and so on, and moving that along the chain. And you see that that's exactly what happens with the operator mixing too, because the structure of the lattice Laplacian is exactly the same. Okay, so we've essentially said that when we have SUN conformal matter, we have operator mixing in this sector controlled by a nice Heisenberg spin chain. So what about the other cases of conformal matter? Well, these rank K conformal matter theories have ADE-SCFT duals, which look like ADS7 times S4 mod gamma, where gamma is a finite subgroup of SU2. And the protected operators that we are considering, which are essentially like long arcs going from the north to south pole on the S4, are not particularly sensitive to the different choices of gamma. So it's reasonable to expect some integrability will persist throughout this. Another way of thinking about this is you have integrability in SUN, n equals 4 Superbeing-Mills. And so adding orientifold to the D3 branes, you would not expect to break that integrability, so you would predict to have it also for the SO n equals 4 Superbeing-Mills. But I'm not going to argue for this too hard. I'm just going to say, okay, let's assume this. That sounds very reasonable. So then we can say, well, we have some evidence for this, but for now, let me assume it. So let me say operator mixing in this sector is controlled by a 1D integrable open Heisenberg XXX S spin chain for S is greater than 1/2. So to determine the dilatation operator, which determines operator mixing, we need to know the spin chain Hamiltonian. And the amazing fact is that once we've assumed integrability of the system, then the Hamiltonian is actually uniquely fixed by like Babujian and the Leningrad School many years ago. And the Hamiltonian looks something like this. Essentially, it's just a degree 2s polynomial in the spin s operators. And this object, Q2s, fixed by integrability, is this rather ugly looking polynomial, depending on your tastes in polynomials. But I write down the expansions for the values of s that we are interested in. And again, I don't know what to make of all of these coefficients, but these are what they are. And we see that when s is greater than 1/2, there are higher order spin-spin interaction terms. Like here, there's a spin-spin squared term. And this is not unexpected from what I said earlier about the fractionation of M5 branes. So this should not really come as a surprise to us that there are higher order contributions. Okay, so now that we have a spin chain, an XXXS integrable spin chain, we can take advantage of the machinery of the beta ansatz to actually start solving and computing things like anomalous dimensions. So let's consider the operator O with I impurities. And now I can be in the spin S, the XXX sub S case. So I have a bunch of momenta of my quasi-particle excitations, and these are related to the rapidities, which are just defined in this way. And the anomalous dimension is then given in terms of these rapidities, or else the energy of the spin chain configuration. Okay, so there are some beta ansatz equations which constrain the rapidities, which look like this. And I didn't tell you about this, but we also have a decoupling equation, which essentially constrains some product of the rapidities to be 1. Okay, so as a final thing, let's actually compute and see something very explicitly. Let's take G equals SUN, and let's take exactly 2 impurities. So these are operators that look like a bunch of x's. I should have put subscripts like x1, x2, a bunch of x's, and then at 2 different locations, we have a y dagger. Okay, so in these operators, there are 2 momenta, as you can just see right here. It's like a sum over I. And the decoupling equation basically tells you the rapidities associated with these momenta, there's just 1 of them, because P1 is minus P2. And if you look at the beta ansatz equation, which was given here, this kind of ugly thing, it becomes very simple in this case because there's only 1 rapidity. And we can see it takes this form, which is nothing more than exponential behavior. So we see that the solution is essentially the roots. P1 is P2 takes these values for m equals 0 to k minus 1. And these are basically the eigenstates. So the anomalous dimensions are now just given via the formula on the previous page once you've worked out what these mu are. And it's basically just there's some coefficient which controls the strength of the coupling, which we worked out from our 1 loop computation. And then it's like 8 sine squared pi m over 2k plus 1. So we see it's very suppressed in the very large k limit. And m just runs over these different possible energy eigenstates. Okay. So what I've told you is that we're computing some anomalous dimensions for some classes of operators in 60 SCFTs. But in the process of trying to answer that question, what we've discovered or learned is that there exists some 1 loop integrability in certain large R-charge sectors of 60 SCFTs. So that's a very surprising result. And in fact, I would even say that as a byproduct of discovering this integrability, we've been able to determine the anomalous dimension of a certain class of nearly protected operators. But the point that I sort of want to emphasize is that, at least in some sectors, we've discovered some integrability. And I think some very interesting questions for the future are, how prevalent is this integrable structure in 60 SCFTs? Does it exist at higher loop orders? At higher loop orders, I can sort of start including next to nearest neighbor interactions and so on. Do I still have some integrable structure? What about if I insert different operators, different kind of impurities, look at different sectors? Can we see some integrability also in those sectors? And then what about connections with ADE-SCFT? So if there is a integrability in the 60 SCFT, you expect that to be reflected in the ADE-SCFT duals. Can we see some hints of that in the duals? And some of these kinds of questions on this integrable structure will be addressed in a forthcoming work with Baum and Heckman. But I'm slightly over time, so thank you for your attention. Actually, it was perfect timing, very good. Thank you for your attention, and I will take some questions if you have any.
All right, thanks very much, Craig, for the excellent talk. We can all thank Craig using our clap emoji. We have time for a couple questions if there are any. If you have a question, just type you have a question in the chat box. While we wait for other questions to roll in, just to make sure I understand, so you're able to carry out this procedure for an arbitrary number of impurities as long as it's small with respect to K, right?
Yeah, exactly. So as long as you can maintain in some kind of dilute gas approximation where the impurities are not all piling up on top of each other, then you still have control over this perturbative expansion in the large R charge. So I never really told you about sort of doing the perturbative expansion explicitly, which is essentially that loop integral, mostly because it's technical and takes some time. But yeah, precisely.
Fantastic, thanks. All right, looks like Fabian has a question.
Hey, Craig, thanks for the talk.
Hey, Fab.
So probably this is obvious from the formula, but it wasn't long enough on display to actually fully digest it. I would have expected that the correction to the pure dimension, so this gamma, whatever you called it, the prefactor is proportional to something like R minus R pure, because of course the correction should go to 0 when the state goes back to the R charge of the pure state. Yeah,
so for example, what I wrote here in terms of the anomalous dimension is that basically delta 0 is the dimension of the pure operator.
Yeah, no, I meant in the integral you had, so where you were computing the gammas. Yeah, here. Or
so like here?
Yeah, here.
Yeah, so okay, so there are slightly different normalizations going on, whereas I think here we did not. So for example, I can show you this in a slightly different way. If you look at this Hamiltonian here, this Hamiltonian basically has this -1/2 here, which is basically subtracting off the contribution from the anomalous dimension of the pure operator, from the dimension of the pure operator. Whereas later on, actually I kept that in all cases. Okay, so in this example, I think that is not yet normalized such that the ground state is 0.
All right, thank you very much.
Yeah.
All right, our next question is from Yinan.
Hi, Craig.
Hey, Yinan.
Actually, I have 2 questions. So first, suppose I just consider D4 conformal matter, which is just a rank-1 E string. So in that case, there are some especially interesting results that you can compare with any existing literature, or are you aware of?
So, well, good. So the new results that we really have are results that occur for basically these very, very long quivers. So for DD type, or the E string, let me just call it the E string for D4 conformal matter. For example, the spectrum is discussed, for example, in a bootstrap paper by Chang and Lin. And there they determine like the spectrum from a bootstrap point of view, and they determine like the scaling dimensions from that point of view. And these kind of X operators that we wrote down match with, for example, what they write there.
Okay, okay. I see. So it matches. And so another question is, can you say anything about the 5D operators like KK0 or any other 5D SCFT from this approach? I think you're using the KK theory.
Yeah, so that's the part that I didn't really tell you about, is that the KK theory is, so the 5D KK theory is what we use to regulate the basically the fact that you don't actually have a coupling which you can tune to be small on the 6D theory. But I don't know what we can say about whether there is any integrable structure in 5D as well. That I have not thought about.
Okay, thanks.
All right, we can take one more question and then we better move on. Our last question is from Ajit.
Hi, Craig. Thanks for very nice talk. I have a question, like, what does it mean to be impurities here, and what correlation it has with the 1D spin chain in terms of impurities here?
Very good. So, so for example, so the pure operator that I wrote down, which is the half BPS protected operator, is essentially the bifundamental operator that looks like this. It's composed of all x's, which are the highest weight of the S equals a half SU2R representation. So by impurity, what we mean is that we consider an operator where you basically insert one Y dagger, which is the lowest weight of the 2 representation of SU2 at some position. So you can think of the x's as being spin plus 1/2 and the Y daggers as being spin minus 1/2.
All right.
And in terms of the spin chain picture, that sort of the statement I just said copies over. So the Y daggers correspond to a spin down state, which is just a spin minus 1/2, and the x's correspond to the spin up states, which is the S plus 1/2. Yeah, so by impurities, I just mean basically the insertions of these Y daggers. And the reason we call them impurities is because we want to consider sort of the pure operator, which we know is protected, and consider things which are not too far away from that. So whose conformal dimension, the contributions to the conformal dimension are still sort of dominantly coming from those of the pure operator.
Okay. All right. Thanks.
Thank you.
All right, Craig, thanks again for the excellent talk. Let's thank Craig one more time.
Thank you.